Hi, students, and welcome to today's lesson. I'm Mr. Simpson. Today, we will explore the question, how can electrical energy be used to move a light rail train? Are you ready? Grab your pencil and your science journal, and let's get started. In our last lesson, we traced the flow of electricity through a light rail train system. We learned that the pantograph helps create a closed circuit. That makes me wonder what types of materials someone could use to make a pantograph. Remember that a conductor is a material through which energy travels easily, and an insulator is a material through which energy does not travel easily. Think about how we could represent a pantograph in a circuit model. What materials could we use to represent the pantograph? Maybe we could use something metal like aluminum foil. We know aluminum foil is a conductor because it can connect to a battery to light a light bulb. Metals are usually good conductors of electricity, but the pantograph in this photograph does not look like aluminum foil. So we should investigate what other materials are conductors. What materials would not work well to represent the pantograph? What about rubber? The charging cord for my phone conducts electricity, but I can touch the cord even while I'm charging my phone because the wires are covered in rubber. A pantograph uses electrical conductors and insulators to direct the flow of electricity. In today's lesson, we will test objects to identify different materials as conductors or insulators. We'll try using each of these materials as the pantograph in our model. The lead from this pencil, a penny, a cotton ball, a towel, a bag closure, an eraser, and a nail. Remember this light rail circuit model? We can use it to test our materials. We will place each material, one at a time, in the spot where the pantograph is on the light rail circuit model to complete the circuit. If a material is a conductor, the motor will turn on. If a material is an insulator, the motor will not turn on. We will put the materials that are conductors on the left side and the materials that are insulators on the right side. As we test each material, shout out whether the material is a conductor or an insulator. Ready? Let's start the investigation. First, we'll test the pencil lead. Pencil lead is made of carbon. Now, the copper penny. What's next? Oh, the cotton ball. It's made of cotton, right? Now we have a towel that's made of glass. Next up, the plastic bag closure. Now we're testing the rubber eraser. Our last material is the steel nail. So the carbon pencil lead, the copper penny, and the steel nail are conductors, and the cotton ball, the glass towel, the rubber eraser, and the plastic bag closure are insulators. Keep all this in mind as we work to learn more about pantographs. Look at this pantograph diagram. The outside of the train, or the train car body, is made of steel, like the nail. In our investigation, we found that the steel nail is a conductor. So we know the train car body is a conductor. I labeled the rest of the diagram for us. Where do you think the conductors and insulators in the pantograph are? Let's write a C next to the parts of the pantograph that are conductors. And let's write an I next to the parts of the pantograph that are insulators. We already know the train car body is a conductor. Do you see any other parts that are made of steel? Point to them. The upper arm, the lifting device, the lower arm, and the base frame, right? Let's label all these parts with a C. Do you think the copper contact wire is a conductor or an insulator? The penny is made of copper, and it is a conductor. So the contact wire must be a conductor too. What about the insulator coils? They're made of glass and plastic. Well, the tile is made of glass, and the bag closure is made of plastic. And they are insulators. So I think the insulator coils are insulators, right? That must be why they're called insulator coils. We only have two parts left to label. Let's label the contact strips next. The contact strips are made of a carbon and copper mixture. We know from the carbon pencil lid that carbon is a conductor, and we already know copper is a conductor as well. Let's label the contact strips with a C. Now let's label the collector head. We don't know what the collector head is made of, but look, it looks like it's the only part of the pantograph that touches the wires. That means electricity from the wires must flow through the collector head. So the collector head must be a conductor. Great. Use your finger to trace the path of electricity from the contact wire to the top of the train. Did you trace a path that looks like this? Awesome. Now let's explain how conductors and insulators work together in the pantograph. Maybe you think that since the electricity needs to get into the train, a conductor needs to touch the wires. I agree. And maybe you said the body of the train is steel, which is also a conductor. So the pantograph might need an insulator on the bottom. That's a great point. Without the insulator coils, electricity would go through the train car body instead of going to the motor. Let's look at this flow of energy in a photograph of a pantograph. The top of the pantograph is a conductor. Electricity flows from the contact wire through the contact strips. Electricity continues to flow from the collector head through the steel arms of the pantograph. The insulator coils at the bottom of the pantograph prevent electricity from flowing into the steel body of the train. Instead, electricity flows into wires inside the train, and those wires direct electricity to the motor. I made this table with the data from our investigation. Point to the materials that are in the pantograph. Carbon, copper, glass, plastic, and steel, right? We learned that some of these materials are conductors and some are insulators. Remember, a light rail system must have conductors and insulators to direct the flow of electricity through the circuit. Let's add our new learning to our class chart. Let's create another section titled Energy. We can add conductors and insulators can be used to direct the flow of electricity in a circuit. Great. Your task after this lesson will be to update the class chart. Think about the energy transformations we observed when we looked at light rail circuit models and investigated pantograph materials. In a light rail circuit model, the motor transforms electrical energy into mechanical energy. And when I touched the battery in this model, right after the last lesson's investigation, the battery was warm. Do you think some of the electrical energy was transformed into heat? I do. We've learned a lot, but are we ready to answer the question, how can electrical energy be used to move a light rail train? I think we need to learn even more. I have a video to help us. As you watch, look for other examples of energy transformation.
Orange line to LBJ Central Station. 2 cars. Safety, please stand by.
What energy transformations do you notice? I noticed that when the train slows down, it makes a sound. Did you notice that too? I think when the train slows down, mechanical energy is transformed into sound energy. And hey, there are a lot of lights flashing, so maybe electrical energy is transformed into light energy. I don't know about you, but I still have lots of questions about energy transformation. In the next lessons, we will explore other forms of energy in the dark rail system. Let's review your task for today. Update the class chart.